Hello guys, welcome back to my channel Gamma Da Gamma. So in this video, I said let's continue the streak of complex integrals that we have already started. And on top of that, this is an improv session. So we'll be doing the problem simultaneously. That's the best part. Let's get started. As always, I'm going to label that I. We have integral from 0 to infinity x cubed times the sine of 4x divided by x to the 4th plus 4 dx. And as I already promised you, this is going to involve complex analysis. So we are going to do that by complex analysis. Although I would like to point out now, you can probably do this, most probably do this with Laplace transforms or Fourier transforms or anything of that sort. Even Feynman integration might work. Now, I didn't give it a try because I already promised you. So anyways, so for complex analysis we need a complex function. So let's generalize this for a complex variable z. The integrand will become z cubed and e to the I times 4z divided by z to the 4th plus 4. Okay, so this is our integrand. Now let's it's actually time to define a contour of integration. So here's the contour that we need. Call this the real axis, imaginary axis. The way we're going to do this is going to go from negative r to 0, 0 to r, and then loop back over gamma. So our contour integral of f of z dz is actually going to be integral from minus r to 0 of f of z dz plus integral from 0 to r f of z dz plus this curvy bit of integral over gamma f of z dz. Now we all know that we are going to do the estimation lemma on this integral over gamma on a fresh page, but before that, one thing to point out, integral from negative r to 0, we can do a slight parameterization. Take z to say be negative z, you'll have negative z cubed e to the negative e to the negative I times 4z divided by z to the 4 plus 4. That's going to be an integrand. We can write that now going from 0 to r, and we'll have a negative by the dz that will cancel out with this guy. But we'll need another negative to correct the order of r to 0 from to 0 to r. So then we'll have a negative again to correct the order, z cubed e to the negative I times 4z divided by z to the 4 plus 4 dz plus integral from 0 to r z cubed e to the I 4z over z to the 4th plus 4 dz plus the part over gamma. Now notice from 0 to r in both the cases, which was originally negative r to 0, we're completely on the real axis. So z equals x plus iy. There is no y, there is no imaginary part, it's all real. So z is equal to x just for this negative r to r. If we do those small changes, we'll have negative integral from 0 to r x cubed e to the negative I 4x over x to the 4th plus 4 dx plus integral over r x cubed e to the I4x over x to the 4th plus 4 dx plus integral over gamma f of z dz. And let's, as I said, do this on a fresh page, estimation lemma. So as discussed before, we have our f of z, integral over gamma dz. But let's consider the mod of that is less than or equal to integral over gamma, but the mod of the integrand now. Now what we can do is we can actually plug in f of z, z cubed e to the I4z over z to the 4th plus 4 mods, surrounded by mods. But gamma is this path, this semicircular path, which has basically goes from 0, if you consider this, to 180 degrees, pi radians. So we can parameterize it this way, and it has a radius of r. Let me point that out. So if I let z equal r e to the it, let's take a negative, and I'll explain why. We'll have, and then let t go from 0 to pi. Then we have a negative r cubed, which is negative r cubed e to the 3it e to the negative 4i r e to the it divided by r to the 4 e to the 4it plus 4. Everything is in mods, don't forget that. dz is negative ri e to the it dt. Okay, so we can just ignore the negatives, we're anyways in mods. Integral from 0 to pi. Mod of e to the it is 1. We just have r cubed. We have mod of e to the negative 4i r e to the it. And the mod of this guy is r, so r to the 4th effectively, divided by, now I want to use a triangle inequality in the denominator, so I can write this as mod of r to the 4th e to the 4it minus mod of 4 and a dt. This is, evaluating this is easy. R to the 4th e mod of e to the negative 4i r e to the it divided by r to the 4th minus 4 dt. And now I would like to take the limit as r goes to infinity. When that happens, well, r to the 4 polynomials of same degree, it doesn't really matter, because again the coefficients of these high order terms is 1. But what is actually going to matter is this negative exponential over here. This negative exponential will make the entire integral, the integrand, to decay to 0. That's the entire reason behind choosing negative r e to the it. That's because then we obtain a negative exponential and everything just cancels off nicely. Which means the mod of this guy is less than or equal to 0. And since the mod can not be negative, it's trapped in 0, less than 0 and greater than 0. So it has to take a value 0. And if the mod of something is 0, which means that something inside the mod is 0. Basic property, beautiful applications. So this path over gamma just became 0. No need to worry about that anymore now. So as is customary, we need to find the residues of f of z. F of z, let me remind you, z cubed e to the I4z divided by z to the fourth plus 4, and we need to find points inside the contour where f of z is basically undefined or it blows to infinity. Those are points basically where the denominator is equal to 0. So z to the fourth plus 4 is equal to 0. We have a complex equation now, and we can write this as z squared plus 2i, z squared minus 2i is 0, but since it was of order 4, we need to have 4 roots. We just have 2. Let's use the difference of squares identity again. Z minus I times square root of 2i, z plus I times square root of 2i, and both of these guys are under root, and z minus square root of 2i, z plus square root of 2i is equal to 0. This is just difference of square identity all over again. So we know we have these 4 points, but in our contour, which was a little bit like this, we can only accommodate the positive ones. Only the positive ones are going to be inside the contour. So square root of 2i will be somewhere like this or something, or not 45 degrees but close to it. Actually 45 degrees, but like having a lesser magnitude. So this is square root of 2i, and I times square root of 2i. When you multiply anything by I, any complex number by, you rotate that by 90 degrees. So 90-degree rotation of this guy, I times square root of 2i. So these two guys are inside the contour, so we need to consider both of them. Ignore the others. So ignore this, because they are negative. They'll be below, not inside the contour. So residue at z equals I times square root 2i. It's simple. What you do is you take the limit as z goes to I times square root 2i. You have z minus I times square root 2i times f of z. So all these things were in the denominator, and this will cancel out with this guy now. We'll have limit as z goes to I times square root 2i, z cubed e to the I 4z divided by z plus I times square root 2i, and these we can again recombine to form z squared minus 2i. Now we can simply plug stuff in. So I cubed is negative I. Cubing this, we'll get 2i times square root of 2i, e to the I and I will negative 4 times square root of 2i divided by 2i square root 2i, and then square of this guy is negative 2i and a negative 2i. Fair enough. Okay, so this is cancelling out with this completely. Negatives can be taken off nicely. E to the negative 4 times square root 2 times square root I divided by a factor of 4i. Now square root of I by Euler's identity is e to the I pi over 2. Square root of I is e to the I pi over 4, which is 1 over root 2 times I plus 1. And you're multiplying by root 2, so this will get cancelled with that. You have e to the negative 4, 1 plus I divided by 4i. We can split this up, e to the negative 4 over 4i multiplied with e to the negative 4i. That is basically residue number 1. Residue number 2 is at z equals square root 2i. So again, repeat the process. So z minus square root 2i times f of z in this limit. These are simple poles of order 1, that's why. You'll have limit as z goes to square root 2i. This will cancel out with one of this factor over here. We can recombine the first two guys. The numerator is as it is. Recombining these last guys, we'll have z squared plus 2i and then z plus square root 2i, because the minus 1 just cancelled out. Now just plug stuff in. So we'll have 2i square root 2i e to the I times square root 2 times square root I divided by square of this is 2i plus 2i, 4i, and we'll have a 2 times square root of 2i over here. This cancels out with that. 2 cancels out with stuff in the denominator. The I can also be cancelled out. We just have e to the I square root 2 square root I over 4, which can be expressed as, again, square root of I is 1 over root 2 times 1 plus I. In case you were wondering how e to the I pi over 4 became this thing, it's because e to the I theta is cosine theta plus I sine theta. Sine of pi over 4 and cosine pi over 4 are 1 over root 2. Just Euler's formula all over again. We'll just have 1 plus I over here divided by 4. Then e to the I, I believe there is a 4. Yeah, sorry guys, this is improv, this happens. 4i times e to the negative 4 divided by 4. That is residue number 2. And our contour integral f of z dz is actually 2 pi I times the sum of residues. So 2 pi I and then sum these two guys together. One small correction, this I will also cancel out with the I in the denominator. So there will never be an I in the denominator. Small correction. As I said, improv happens, guys. So then we take residue number 1, which was e to the negative 4 e to the negative 4i over 4, and you add that with this guy plus e to the 4i e to the negative 4 over 4, and notice there are some common factors. Take out a 2 and e to the negative 4, 2 pi I over 2 e to the negative 4. We'll have e to the 4i plus e to the negative 4i over 2 because we took 1 2 outside. Now this is just the formula for the cosine. Cosine of 4i. Again, this derives from the Euler's formula, this guy. You take e to the negative I theta, you get cosine theta minus I sine theta. Add this guy to this guy, you'll have a formula for cosine. That's exactly this formula. Cancel this guy out. We'll have pi, I pi e to the negative 4 cosine of 4. No I. That's the contour integral value f of z dz. Now let's go back and see the big picture. We know all the small pieces, the minute details. This was contour integral f of z dz, we know the estimation lemma went to 0 as soon as we took the limit as r went to infinity. So we need to take that here as well. This goes to 0. We know the value of the contour integral, that's I pi e to the negative 4 cosine of 4. Now we have integral from 0 to infinity x cubed. I'm combining both of these, e to the I 4x minus e to the negative I 4x divided by x to the 4 plus 4 dx. Now I would like to divide and multiply by 2, because this difference of exponentials e to the I theta minus e to the negative I theta over 2, and I'll divide by I as well, over 2i. This is precisely sine of theta by Euler's identity. E to the I theta is cosine theta plus I sine theta by this identity, and if you take the negative variant of that and you take the difference of them and divide by 2i, you get a formula for the sine. That's precisely why I'm doing that, because now I have I times pi times e to the negative 4 cosine 4 being equal to 2i integral from 0 to infinity x cubed. This difference of exponentials divided by 2i is sine of 4x divided by, I have to put the bracket here, x to the 4th plus 4 dx, which is precisely our I, capital I times pi times e to the negative 4 cosine of 4. I's will cancel out. I will then be pi over 2 e to the negative 4 cosine of 4, which has an approximate value of negative 0.0188054. Yes, that's a negative integral, believe it or not. Finally, it's really elegant, really elegant. So yeah, if you want to finally write it down, integral from 0 to infinity x cubed sine of 4x over x to the 4th plus 4 dx has a value of pi over 2 e to the negative 4 cosine of 4. The pi again drops in because of the 2 pi I factor. Exponential comes in because of generalization of the sign. Cosine is an added bonus. But I hope you understand why this contour doesn't work. A contour of 90 degrees. That's because if I do that, I will have to, there's no problem from 0 to r, that will directly be our I. But then again, going from this semicircular path, rather half of a semicircular path, again we can use estimation lemma, but going on this imaginary axis, we'll have to take z as ix, and when you use that parameterization inside f of x, you will end up with negative I x cubed e to the negative 4x over x to the 4th plus 1 dx from 0 to infinity. And this is really hard to do because this is a regular exponential, it's not even imaginary. It doesn't have an imaginary argument. That's why this 90 degree contour won't work. This 180 degree will work wonders. Although we had two poles, over here you'll only have one pole, square root of 2i. Here we had square root of 2i and then 90 degrees to that, because multiplying by I is rotation by 90. I times square root of 2i. We summed over the residue over these poles and then came to this nice answer. I hope you enjoyed this video, guys. Please excuse if I made any small errors because it was an improv session. We all make errors. So yeah, I hope you enjoyed. Please like and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. And in the meantime, stay home, stay safe. Stay tuned to my channel and Peace out, signing off.